Alright, hi everybody. Welcome to the last segment of the Fourier series in complex form, or exponential as well. What I want to talk about a little bit is a concept that's not too fond of for mechanical engineers typically. Okay, I'll talk about the fundamental frequency, I'll talk about the period, I'll talk about angular frequency, I'll talk about frequency spectrum, but I think it will give you the flavor. Fourier series, if you have noticed so far, defines a periodic function, right? And if I have interested in the fundamental period of this, fundamental period of a function, which we defined in minus p to p, it's going to be 2p, right? Because we go from minus p to plus p, right? And also you may remember this from your other courses as well, but if I'm interested in the frequency that corresponds to that particular period, then I will actually go ahead and do this. F is equal to 1 over t, where t is basically the period, okay? And you can see over here it's going to be 2p, 1 over 2p is my fundamental frequency. Actually, let's just write, frequency, and you refer to my videos. And also another thing is the omega, which is known as the fundamental angular frequency, and that is defined as 2 pi f. Okay, so from here you can see 2 pi times 1 by 2p. I get myself nice pi by p, right? And sometimes, as you know, we define these with respect to minus pi to pi as an example, so then this will be 1 in that particular example, all right? So if I'm interested in now the Fourier series expansion that we have done, we can do this way. F of x will be equal to a0 by 2, there's nothing I can do about it, summation from n is equal to 1 to infinity. I'm writing the traditional Fourier series, all right? An times cosine of, right, n pi x by p, right? So I'll write n omega x. Well, I will note to you that this is going to be right up here. See? Okay, so plus sine of the same one, n omega x, right? So this will be my traditional or regular Fourier series expansion. If I do this for the complex, what I will get is it will be actually a little bit more straightforward as well. I will have Cn e to the I n omega x. Similar, right? I just have an I up there, right? One thing to note is, let's look here. It's a little bit more easier to explain. You can see over here, I have a Cn, and the Cn is tied to a particular n omega. As n changes, I will have another Cn, and I will have another n omega, right? So what we do, especially the electrical engineers, what they do is they define this absolute value of Cn, and there's a corresponding that for each n omega. They call this the frequency spectrum. Okay, this is called the frequency spectrum. If I want to plot this, and I'll do an example to illustrate this for you. Okay, but the frequency spectrum is when I have, let's say, n is equal to 1, so it's going to be omega. I have a particular amplitude of my signal, and I have n is equal to 0, n is equal to 1, n is equal to 2, so I'm going to plot that, and I'll show you how to do it, okay? But the plot of this is a function of omega frequency spectrum, right? That's what we have. So also, I said it briefly, but this in electrical engineering, this Cn is the amplitude of the n omega component of the electrical signal. So it's an amplitude, all right? Okay, let's solve an example, and I will illustrate these points as well. But also, the example will be handy because I will introduce you hyperbolic sine, hyperbolic cosine, etc. Okay, so this is a good one. So basically what I'm interested in, I want to expand this f of x is equal to e to the minus x in this particular interval that I have, and the expansion should be done in a complex Fourier series, all right? So I'm looking at the notes from my previous segment, and I have the Cn to be defined this way. 1 over 2p minus p to p f of x e to the minus I n pi x by p dx, all right? So, okay, the first thing I always do is I want to investigate what p is. It's going to be pi, right? So it's going to be fairly straightforward. So if I rewrite this, I'll get 1 by 2 pi minus pi 2 plus pi e to the minus x, which is my f of x, times e to the minus I n pi by pi x dx. So pi's cancel, you've seen that here, right? Okay, that's good. So let's do this. I'm kind of going ahead and solving this while I'm at it, right? So I will have this minus pi to pi. I will combine these powers. Let's see how am I going to get that. Negative is in both of them. So ni plus 1x. You've seen that, right? So I simply go ahead and combine minus I and x, minus I and x, and I have minus x minus x. Then I think I'm ready to take the integral of this, which will be 1 by 2 pi. It's going to be minus 1 by ni plus 1 e to the minus ni plus 1 x. I need to let this from plus pi minus pi down there. Okay. So if I rewrite this, then I'll get 1 by 2 pi ni plus 1. So if I put pi, I will get myself e to the minus ni plus 1 pi minus e to the minus pi. Minuses cancel, so I'll get myself ni plus 1 pi. Okay. So now I'm just now working to have a better version of this to easier for me to work out. So now what I'm going to do is I will distribute this. So I'm going to get minus e to the minus pi times e to the minus ni pi minus e to the pi times e to the plus ni pi. Okay, I am progressing nicely towards an answer. 2 pi ni plus 1 e to the minus pi. Do you remember this from the previous segment? I said that this is going to be cosine n pi minus I sine n pi. Sine n pi was 0, so I will get myself minus 1 to the power of n. Okay, so you may want to review the previous segment. I have done this, right? And I will let's go back to the original color, minus e pi, and I also did this one as well, and that one turned out to be minus 1 to the power of n as well. Okay, so you may want to again review that and then close the parentheses. Okay, let's rewrite this. Minus 1 to the power of n. So I'll change the order of these two, so I want to get rid of this negative. Divided by, you'll see why I put 2 inside of the parentheses momentarily. E to the pi minus e to the minus pi by 2. I mentioned that we will obtain a sine hyperbolic, right? This is sine hyperbolic of pi. Okay, so something to note. So I actually will talk in about a minute about cosine hyperbolic, tangent hyperbolic, just as a prerequisite knowledge kind of deal. So minus 1 to the power of n divided by pi ni plus 1 times sine hyperbolic pi. Okay, so this is it. This is my Cn. So basically, this is my Cn value. And if I want to write this in the fx, then I will write the rest is fairly easy. Minus infinity to infinity. I have my Cn, which is minus 1 to the power of n divided by pi ni plus 1 sine hyperbolic pi, and then I will have e to the power of I and x. That's it. So this is my f of x. I will go ahead and do the frequency spectrum, but before that I want to talk a few minutes about this sine hyperbolic. You have seen this over here. Sine hyperbolic of x is equal to e to the x minus e to the minus x by 2. Let's write while at it cosine hyperbolic x as well. So that's going to be e to the x plus e to the minus x by 2, right? Tangent hyperbolic x, you may think this is going to be sine divided by cosine, right? This divided by that, you would think, and you will be right. Okay, that's what it is. E to the x minus e to the minus x divided by e to the x plus e to the minus x. Those cancel, and then you can prove this to yourself at home. But cosine square hyperbolic of x minus sine square hyperbolic of x is equal to 1. Okay, in the regular one it's for plus sign, it's a negative sign. Just want to highlight that. All right, so this is something that I recommend that you kind of know. Okay, now let's going back to the frequency. Okay, stuff that we talked about. I want to get the frequency spectrum of this, but let's look at the period. Okay, that's the first thing that we need to do. So the period, I'm gonna write this over here. it was going from minus pi to pi, right? So from here, my f turns out to be 1 over 2 pi, right? And if I want to write my angular frequency from here, you can see that then that's going to be pi by p is pi. So I will get 1, okay? The angular frequency of this particular one is 1, okay? So that's something to note. So let me go down and let me now investigate this Cn as a function of the omega, right? So, okay, so basically the goal here is to obtain this Cn, absolute sign of the Cn. So let's just, remind of ourselves, this is going to be minus 1 to the power of n divided by ni plus 1, and then it will be sine hyperbolic pi by pi. I need to take the absolute sign of this. Okay, the question is, what will be the absolute sign of this? Minus 1, it is either minus 1 or plus 1. So at the end of the day, I mean, you've seen it, this goes away, this becomes 1 basically, okay? And what about that? We know that, it's going to be square root of n squared plus 1, square root of it, right? And I can't do much about hyperbolic sine pi divided by pi, so that's going to stay right there. So if I rewrite this, you will see that my Cn now will be 1 by square root of n squared plus 1, square root of it, times the sine hyperbolic pi by pi. And as I mentioned, the plot of this, what you're looking at this screen, will give me the frequency spectrum. So if I do plot like this, let's say here, okay, and let's say obviously this is 0, this is omega, 2 omega, 3 omega, and let's also have symmetric. Wow, I didn't do a good job, so it's going to be hard to do symmetric, something like that, minus 2 omega, minus 3 omega. So basically I need to plug this into my calculator. If I have n is equal to 0, so this is going to be basically sine, so if I have this amplitude like that, you will see that this amplitude at n is equal to 0 right over here will be this, right? Hyperbolic sine pi divided by pi, okay? And if you punch this in the calculator, you're going to see a little bit above 3.5. That's not the point, okay? But just to have an idea. And then if I put n is equal to 1, you will get something like this, you will get something like that, and then it keeps dropping, okay? So this will be your frequency spectrum for this particular case. Obviously, this goes to infinity, right? Okay, that's all I have for the complex Fourier series, as well as the period, angular frequency, frequency spectrum concepts, okay? I'll be back with Sturm-Liouville problem. Take care.